Assalamu alaikum everyone. I hope you all are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and you are watching Science with Ali. This is part number 5 of redox reactions. So a quick recap of what we did in part number 4. We first started off with a chemical equation and described what is being reduced and what is being oxidized. Then first we moved on how to deal with a radical. For example, if a radical remains the same before and after the reaction, we will denote that radical with its relative charge. For example, sulfate here has a charge of -2 because it is the same before and after the reaction, or we can say that it is present before and after the reaction. And later on we also discussed some radicals. These are a few examples. You need to learn all of them, the relative charges as well. So we discussed an equation which told us that OH is present in this reaction, but there was no OH present on the other side of the reaction, meaning that the radical changed after the reaction. So we will consider oxidation number in this case for oxygen and hydrogen separately because there is no OH on the other side. Then we spoke about how to easily identify if a reaction is non-redox, like there is no element over here and it is a non-redox reaction. A reaction which does not include an element will be a non-redox reaction. Then we discussed a few chemical equations relating to non-redox reactions as well, and we did some equations as well. Now I left you with these 3 equations. I hope you have understood them and have solved them as your homework. So let's get into it. So the first equation that we have here is the first step to a redox reaction equation is to look for the elements. So there's no element on the reaction side, but I can see oxygen over here. So oxygen is an element. So we will go ahead and write down a 0 as its oxidation number. Now, I know that nitrate is a radical. I can see a nitrate on the reactant side, but I cannot see another nitrate anywhere here on the product side. Because of this reason, I have to consider the oxidation number for each element in this radical separately. So let's go ahead and solve it now. So we have nitrate first, NO3 minus 1. Now I did tell you in the last class that we do not need to do the whole zinc nitrate because it is just going to make things more complicated. So why not just take out NO3 minus 1 and solve to get what nitrogen's oxidation number is. But anyway, before we solve this, let's just go ahead and write down the oxidation numbers for the rest of the compounds over here. It'll make things easier to understand. So on the product side, I have oxygen, so it's a -2. Nitrogen we need to find out. Oxygen also here is a -2, and because zinc is a transition element and does not have an oxidation number, it will have to be a +2 in order to make the compound a 0. Okay, so moving on to this side, it will be oxygen will be a -2, zinc will always be a +2. Right, so let's solve for nitrogen in this compound. Okay, so oxygen is a -2. This is x. So x -2 times 3 is equals to -1 because the overall charge of nitrate is a -1. Alright, so let's just solve it. X minus 6 is equals to -1. X6 will go on the other side to become +5. So x is +5. Alright. Right, now let's go ahead and write down the oxidation number for this regular compound. We can just do this very automatically. This is -2 times 2 is -4, and this is x is equals to 0. So -2 times 2 is -4. It will go on the other side to become +4. Alright, so nitrogen is a +4 over here. So what is being oxidized and what is being reduced? I think it's pretty clear. Zinc is remaining the same. As I told you, to isolate one element at a time and look for it on the product side. So I can see nitrogen is going from a +5 to a +4. So nitrogen is being reduced because a reduce in oxidation number is reduction. So this is getting reduced. And as for what's being oxidized, I can see oxygen is going from a -2 to a 0. So -2 to a 0 is an increase in oxidation number. So we will go ahead and write down that oxygen is being oxidized. Right. Now moving on to the second equation that I gave you. First step, to note down the elements. Magnesium is an element, hydrogen is an element. Now I can see that there is a radical NO3 and NO3 on both sides. So considering what we did in the last class, NO3 is a -1, right? So we will just go ahead and write down -1 for the whole of this compound. So nitrogen is also a part of this. So hydrogen is a +1, magnesium is a +2, and now we'll just go ahead and write down what's being oxidized and what's being reduced. Magnesium is 0 over here, it is a +2, so it is being oxidized. As for hydrogen, it is a +1 over here and a 0 over here, so it is being reduced. As for nitrate, we just say that it is a -1 and we just go ahead and ignore it because it's the same before and after the reaction. Okay, so hydrogen is being reduced. Moving on to the third and last equation that I gave you for your homework. So let's just go ahead and write down the elements. Oxygen is an element, and that's it. Now CO2, it's a -2 over here, so -2 times 2, and there's X over here. -2 times 2 is -4 is equals to 0. -4 will go over here, so it's going to be a +4. Okay, so it's going to be a +4 for carbon. As for water, it's very simple. It's a +1 over here and a -2 for oxygen. Let's go ahead and write down what's being oxidized and reduced. So carbon is going from a -4 to a +4. It's a very drastic change for carbon. So it's being oxidized because it's an increase in oxidation number. As for hydrogen, it's going from a +1 to a +1, so it does not change. Oxygen is going from a 0 to a -2. So it does not matter if you're going to make the arrow over here or make it over here. It just has to be correct, right? So -2 will just go over here. It's being reduced. So I hope you were able to sort this question out very well, because we have done these questions multiple times. If not, I would like you to rewind the video and then solve the equations and try to solve the equations again, and pause the video before I solve it, so you have a better idea of what we are doing here. So having said this, we are now moving on to the last topic of this chapter, which is oxidizing and reducing agents. Alright, so in order for you to understand this term, I am going to be using an equation which we have already done before in part number 2. Let's just go ahead and write it down. 2Na plus Cl2 will give me 2NaCl. Right, now there are a few basic things which we are now very familiar with, and that is putting oxidation numbers and figuring out what's being oxidized and reduced. So let's just do the same over here. I hope it's pretty simple of what we've done over here, right? So Na is a 0, it's an element. Cl is a 0, it's an element. Cl is a -1 and Na is a +1. Na is being oxidized and chlorine is being reduced, right? That was pretty easy. Now I have a very simple question. Why is sodium oxidized? Like, how did sodium go from a 0 to a +1? What happened to the electrons of sodium that it became a positively charged ion? Now we know that sodium has undergone loss of electron. It is going from a 0 to a +1. So it is oxidized, and chlorine has gained 1 electron as it goes from a 0 to a -1. So it is reduced. We know that. Now one question, why is sodium even losing that electron? Why does it even need to lose that electron? Because it has chlorine available to gain that electron. That being said, if chlorine was not present here, would sodium have lost that electron? Of course not. So if sodium wants to lose that electron, it is mandatory for chlorine to be there. If chlorine wasn't there, so sodium would not have lost that electron. So it is because of chlorine that sodium is being oxidized. It's the chlorine that enables sodium to lose its electron, and hence sodium would not be able to get oxidized either. So chlorine is the primary reason of sodium's oxidation, which is why chlorine is the oxidizing agent. Okay? Chlorine is the oxidizing agent. Now, what do you mean by an agent? For example, a travel agent, it makes you travel, for example, and it's the agent that gets a certain work done. So in this case, it is chlorine, which is an agent that gets the oxidizing of sodium done. In the same way, chlorine is getting reduced. Why? Because of sodium. Chlorine is only getting reduced because sodium is losing its electron, and chlorine is there to gain that electron. Chlorine is present to gain that electron. So we can say that sodium is a reducing agent. Now, there is a simple assumption: the substance which is getting oxidized itself, for example, sodium is being oxidized, is the reducing agent, and the substance which is getting reduced itself is the oxidizing agent. So it's basically the opposite. So if we pen this down, we can say that in a redox reaction, the substance that is oxidized is always the reducing agent. We call it the reductant also, reductant, and the substance that is getting reduced is always the oxidizing agent. So I basically just copy pasted the statement and changed these simple words, right? Now the substance that is reduced is always called the oxidant. Okay, just take it as well. Now, in order for more clarity, we will now do one equation and try to find out the agents in this particular equation. So we have here zinc plus sulfuric acid gives us zinc sulfate and hydrogen, right? So now we need to know the oxidizing agents, but we need to find out what's being oxidized, what's being reduced over here. So hydrogen is a 0, zinc is 0 because of elements. Sulfate is present on both sides, so it will be a -2. This is a -2, zinc is a +2, and hydrogen is a +1. So zinc is being oxidized and hydrogen is being reduced. Now, considering what we have written over here, is that the substance that is being oxidized is always the reducing agent, and the substance that is reduced is always the oxidizing agent. We can just go ahead and write down that zinc was your reducing agent because it's being oxidized, and hydrogen was your oxidizing agent because itself it was being reduced. Pretty much your working is the same, but with the addition of just one more thing. Always remember that it is always the opposite. It's being oxidized, so it's a reducing agent. Is being reduced, so it's an oxidizing agent. The agents are always the opposite of what's truly happening to the element in the chemical reaction. Now, up till now, we have discussed the oxidizing and reducing agents in two particular reactions. In the above reaction, we concluded that zinc and hydrogen are the agents, And in the above reaction, chlorine and sodium are the agents. Primarily in the real world, in labs, in chemistry labs, in hospitals, etc., we use specific oxidizing and reducing agents in reactions to carry out redox reactions. There are two of them we need to discuss. So first let's first discuss what our oxidizing agent is, right? So the first agent that we have is acidified aqueous potassium manganate 7. And the formula that we have to display all this is KMnO4. Now you might be thinking, what in God's name have I written over here? It's actually very simple. Now we have done this particular example in a previous video. I think it was part 2, in which we found out the oxidation number of manganate in this particular formula. So let's just go ahead and write down the oxidation numbers. It's -2, it's a +1, we did X. Now if we solve for X, we will get a 7. Hence the 7 is written over here, because manganate is a transition element, and we know that transition element does not have a group number and an oxidation number, so we need to find out. So in this case, I will get manganate as a +7, right? So that's this part sorted out. What's with the acidified aqueous thing? Now aqueous is written over here because it is soluble in water. I hope that's clear. As for the acidified, now in order for KMnO4, potassium manganate 7, to behave as an oxidizing agent, I need to mix it with some acid. Now acid contain H plus ions, right? By the way, this can be any type of acid, be it sulfuric, nitric. It just needs to be an acid, and it just needs to be, because it's an acid, it just has to have H plus ions present in it. Now, when this whole mixture works as an oxidizing agent, it is the manganese that gets reduced. Like so, the manganese gets reduced, oxidizing agent. Hence, it is called an oxidizing agent. Now you do not need to remember this, but manganese gets reduced from a +7 to a +2, so a decrease in oxidation number, so it is decreasing, it is being reduced. So here, when manganese is a +7, it has a purple color, right? Now when it gets reduced, it becomes colorless. Right now, if I show colorless, it's going to be literally colorless, so you just visualize it, okay? So this oxidizing agent gives us a color change from purple to colorless, because it's a transition element, and transition metals have colored compounds, form colored compounds, so that's why we're getting a purple color, and when it gets reduced, it's becoming colorless. Now, in order for you to explain this more clearly, I have a beaker over here, all right? And in that beaker, I have some ethanol, which is an alcohol. So the initial color of this solution is colorless, right? Because alcohol is colorless, right? MnO4, acidified aqueous potassium manganate 7, is a long name. So if I add in this KMnO4 and I heat this by providing heat, I heat this, the initial color after adding this compound will be purple, right? So this whole solution will turn purple, okay? Let's just color it purple, right? So now when we start to heat this, manganese will get reduced and ethanol will become oxidized. Eventually, all the purple color will change to colorless as manganese is getting reduced at the same time oxidizing the ethanol. Now, what do you get when you oxidize ethanol? You don't need to know this. This was just an example. You get carboxylic acid. In this case, we used ethanol. So we got vinegar by oxidizing it, right? We did it by oxidizing it. Okay, and this will change to colorless again, right? This is now vinegar. I hope that's clear. So now we're going to move on to our second oxidizing agent, which is called acidified aqueous potassium dichromate 6. The formula of this compound is as follows: K2Cr2O7. Okay, so let's just note down the oxidation numbers. It's a plus -2, it's a +1, belongs in potassium. Now the 6 belongs to chromium because chromium is a transition metal and transition metals have a variable oxidation state. So it has a +6. Now we also did solve this compound. I think it was also in part number 2. So you can go ahead and check it out for yourself how we did it, how we solved using the variable x, and then the whole compound is equal to 0. So +1 plus x into 2 and -2 into 7 will give us +6 for chromium. Because this particular compound is acidified as well, so we need to add acid in order for it to behave as an oxidizing agent. And in this reaction, chromium gets reduced. Let's just write it down. Chromium gets reduced. So for your information, you don't need to learn this, but there's no drawback in doing so. It goes from a +6 to a +3. Now the color change for this compound is an orange to a green color, right? So green. Now if I go back to this particular example again, but now I will add K2Cr2O7 in place of KMnO4, and we're going to change this back to ethanol, right? So when I add K2Cr2O7, the initial color of this particular reaction will be an orange, okay? Because ethanol is again transparent, and if you add the oxidizing agent, it will become orange. Now when I heat this, chromium is going to be reducing, and at the same time it is going to oxidize the ethanol, hence converting it into vinegar. Now when all of the ethanol is oxidized, it will literally just turn this particular reaction mixture into a green color, okay? This will make sure that all of the ethanol is oxidized, hence turning it into vinegar. I hope that's very, very clear. So what do you even need to learn from this? You just need to learn the formula, the name, and the color change that takes place when we use the oxidizing agent. For in this case, it was orange to green, and in the case for KMnO4, it was purple to colorless, as we wrote over here. Now we will move on to reducing agents. Okay. Now, in order for you to explain this, in order for me to explain this to you, I need to go back a little bit and show you this reaction once again. Now, in this particular reaction, I used ethanol and used an oxidizing agent, added it to ethanol, and I got vinegar. Now, if I want ethanol back from the vinegar that I just produced, what do you think that I need to add? Of course, it will be a reducing agent. To get ethanol back from the vinegar, I need a reducing agent. So it's basically the reverse of what we did for the oxidizing agent. So the first reducing agent that we will be looking into is aqueous potassium iodide. Alright, the formula for this compound is as follows: potassium and iodine, and it is aqueous. So what's happening in this particular compound that makes it a reducing agent? It contains iodine, right? It contains iodide, to be precise. It contains two of them. So what happens is iodide gets converted into iodine, and because iodine is an element, it has an oxidation number of 0. So as you can see here, it is going from a -1 to 0. So iodine is being oxidized, meaning, and anything that gets oxidized itself is always the reducing agent. So that's why aqueous potassium iodide is a reducing agent. Now this also has a color change. The color change in this particular reaction is iodide is colorless and iodine is a brown / dull black. This is the color change that takes place when this particular reducing agent is used. Aqueous potassium iodide is used. So the next two reducing agents that we will going to talk about is carbon monoxide. Let's go change carbon monoxide gas and sulfur dioxide gas. Okay, now what makes carbon monoxide gas a reducing agent? Basically what happens is that carbon monoxide changes to carbon dioxide. Since carbon is getting oxidized over here because it is gaining oxygen, or if we explain this in terms of oxidation number, oxygen is a -2, oxygen a -2 over here as well. Now carbon is a +2 in order to neutralize the whole compound to make it 0, and carbon is a -4 over here, a +4 over here, sorry. So as you can see here, carbon is getting oxidized. So we can say that carbon monoxide gas is a reducing agent. Now in the same way, in exactly the same way, there is another gas, sulfur dioxide gas. So the formula for this is sulfur dioxide, and it gets converted into sulfur trioxide. Okay, so in this we can also write the oxidation numbers as follows: -2 over here, -2 over here. So -2 times 2 is -4. Sulfur has to be a +4, and in this reaction -2 times 3 is -6. So sulfur is a +6. Now sulfur is also getting oxidized, and hence this is deemed as a reducing agent as well, because anything that gets oxidized is a reducing agent. So this wraps up all the oxidizing and reducing agents that are used in this chapter. With this, our chapter for redox reaction has come to an end. If you still have any confusions in this chapter, I have made a playlist in the playlist part of this section called Redox Reactions, in which I have by sequence uploaded all of the chapters, all of the parts of the redox reactions, in which you can check them out as well. And if you have any questions regarding this lesson, just drop them down in the comment section below, and I will try to respond to each and every one of your queries. So with that, this concludes our chapter, and I will see you in the next video.